This meeting is now being recorded.
Hello, and welcome to the 10th session in the Measurement Error webinar series. I'm Amy Subar, a nutritionist with the U.S. National Cancer Institute. In today's webinar, we'll focus on combining instruments as a strategy to reduce measurement error in dietary intake data. Because today's presenter, Doug Methuen, is on travel, we had initially planned to play back a pre-recorded version of his presentation with a live question and answer period. Fortunately, Doug is now able to join us live for the entire webinar, and so today's presentation will be broadcast over the phone as with previous webinars. The audio will not be broadcast over your computer speakers. To hear the audio, please stay on the teleconference line throughout the webinar. Before we get started with today's presentation, please note that the webinar is being recorded so that we can make it available on our website. All phone lines have been muted and will remain that way throughout the webinar. Please use the chat feature to submit a question for the question and answer period following the presentation. A reminder that you can find the slides for today's presentation on the website that has been set up for the series participants. The URL is available in the notes box at the top left of the screen. Other resources available include the glossary of key terms and notation and the recordings of the preceding webinars. Now, I'd like to introduce the presenter for today's webinar. Doug Methuen is a mathematical statistician in the Biometry Research Group, Division of Cancer Prevention at the National Cancer Institute. Doug has worked with other members of the Surveillance Measurement Error Group at the National Cancer Institute over the past several years to develop the NCI method and to extend the method to more complex applications. As I mentioned, today, Doug will discuss combining self-report instruments to reduce the effects of measurement error. Doug?
Thank you, and welcome to today's webinar about combining self-report dietary assessment instruments to reduce the effects of measurement error. In particular, we'll be talking about reducing the effects of measurement error for assessing diet-health relationships. This series is dedicated to the memory of Arthur Shatskin, a colleague who worked with us for many years on the problem of measurement error in dietary assessment. And here is a list of everyone involved in this webinar project. Today's learning objectives are to understand how measurement error leads to loss of precision in estimating diet health associations, to learn how to combine self-report dietary instruments to regain precision and improve power to detect associations, and finally, to understand the limitations of such an approach. First, we're going to talk about why we would want to combine self-report instruments. As we've learned in previous webinars, measurement error in self-report dietary instruments causes three problems. First, it leads to bias or attenuation in estimated diet health associations. Second, it leads to loss of precision in estimated associations. By loss of precision, I mean that the ratio of the expected value of the estimated association to its standard error decreases. This makes it more likely that the confidence interval will include the value 0, which leads to the third problem, which is the loss of power to detect diet health associations. We've also learned that statistical methods like regression calibration can correct for bias due to measurement error, but these methods do not typically recover lost precision or power. There are ways to improve precision and power. One approach is to increase the sample size. This approach has been taken in a few very large cohorts, including the NIH-AARP Diet and Health Study in the U.S. and the EPIC study in Europe, each of which has over 500,000 participants. Another approach is to try to decrease the measurement error in reported intake. One can do this by improving existing dietary instruments or developing new ones. And a lot of work has been done in this area. Alternatively, one could try to combine different dietary instruments to obtain a better measurement of true intake. And this is the approach we're going to take today. Examples of self-report dietary instruments that could be combined are the Food Frequency Questionnaire, 24-hour dietary recalls, and multiple-day food records. Each instrument has its own strengths and weaknesses. One of the problems with food frequency questionnaires is that the cognitive tasks required to complete them are more difficult than those required for the 24-hour recalls or food records. Because of this, food frequency questionnaires tend to be more biased for estimating intake than 24-hour recalls or food records. On the other hand, 24-hour recalls and food records are designed to estimate short-term intake and as a result have large within-person variation or day-to-day variability. Food frequency questionnaires are designed to estimate usual intake, and so they have smaller within-person variation. We believe there is potential for significant gain in precision by combining instruments that have different types of information. For example, one can combine a food frequency questionnaire, which measures long-term diet but can be biased, with a 24-hour recall, which is less biased but has large day-to-day variability. A problem with such an approach is that traditional 24-hour recalls and food records are expensive to administer and or process. As a result, they have not been practical for use in large cohort studies. Recent developments in dietary assessment, however, have made this less of a problem. New automated self-administered 24-hour recalls have been developed, such as the ASA-24 developed at NCI. There are also new automated food records, including some that use mobile phone technology to allow participants to photograph their food before it's eaten and then photograph the leftovers. These new tools are much less expensive than the traditional 24-hour recalls and food records, so they're practical for use in large cohort studies. Now we're going to talk about using regression calibration to combine self-report instruments. Regression calibration is a method to correct estimated diet health associations for bias due to measurement error in intake. The advantages of regression calibration include it's relatively simple and intuitive to use. It's applicable in many situations, such as linear and logistic regression and survival analysis. It's often nearly as efficient as maximum likelihood estimation, and especially important for our purpose, it extends naturally to combine multiple instruments. We're going to begin with a short review of regression calibration before describing how it can be used to combine multiple instruments. We'll assume that our diet health model is a logistic regression model. In logistic regression, the health outcome y is a binary variable that equals 0 or 1 to indicate whether or not some health event has occurred. The odds that y equal 1 is defined as the probability that the event occurred divided by the probability that it has not occurred. The logistic regression disease model assumes that the log of the odds is equal to a linear function of true dietary intake, T. The parameter alpha T is called the log odds ratio, and it quantifies the relationship between true dietary intake and the health outcome. In dietary studies, we are unable to observe true intake. However, we can observe reported intake, which we call R. To perform regression calibration, we need a prediction equation. Here, we have an example of a linear prediction equation where the predicted value of true intake T is a linear function of reported intake R. The regression calibration method is to replace T with its predicted value in the diet health model and then perform the standard analysis. In statistical terminology, the predicted value is called the conditional expectation or conditional mean of true intake given reported intake, R. The conditional expectation is known to be the best predictor of T given R in the sense that it minimizes the mean squared error. The main assumption of regression calibration is that reported intake R has non-differential error with respect to disease Y. This means that reported intake provides no information about disease Y beyond that which is already provided by true intake. Under this assumption, regression calibration estimates are approximately unbiased. The predicted value of T given R, however, provides no more information about true intake than R itself, and as a result, regression calibration does not recover power lost due to measurement error. So let me clarify this a little bit. For linear regression calibration, when you have a single dietary exposure, it's strictly true that you cannot recover any of the lost power. If you have multiple dietary exposures, however, you may sometimes increase power by reducing residual confounding. But this doesn't happen in general. So in general, regression calibration does not recover lost power due to measurement error. So we ask the question, can we make regression calibration more powerful? We know that if we can improve prediction of true intake, then we can increase precision and power. By improving prediction of intake, we reduce measurement error, which in turn improves the power to detect diet health associations. Now, one of the things I said earlier was that conditional expectation is the best predictor of true intake. So how can we improve precision if the regression calibration predictor is already the best? Well, the answer is that the conditional expectation is actually the best predictor of true intake given reported intake, or given the information that's provided. So we can improve prediction by adding information. This leads to the idea of enhanced regression calibration, which is sometimes called extended regression calibration. In enhanced regression calibration, we add an additional variable C to the prediction equation for T. This additional variable has to fulfill two criteria. First, it helps predict true intake. Second, it's not related to the health outcome given true intake. Another way of saying this is to say that C is not a confounder. We can also say that C has non-differential error with respect to the health outcome. Now, the second requirement is crucial because if C is related to intake, then the estimated diet health association will be biased. Since we usually assume that self-report dietary instruments have non-differential error, additional self-report instruments seem to be the perfect candidates for enhanced regression calibration. So, here's an example of enhanced regression calibration. In this example, we're going to combine two 24-hour recalls and a single food frequency questionnaire. Our main assumption is that the 24-hour recall is unbiased for true intake. In earlier webinars, we described regression calibration when the FFQ is the main instrument and the 24-hour recall is used as a reference measure to calibrate the FFQ. Here, both the 24-hour recall and the FFQ are considered main instruments. That is, they're completed by everyone in the study and they're used to predict true intake. In this case, the 24-hour recall is going to act both as a main instrument and the reference measure. So things are a little more complicated than they were before. Like before, however, we have a prediction equation. But in this case, the prediction equation is a weighted average of the mean of the two 24-hour recalls and the predicted value of T given Q. The weights W are a function of the within and between person variance in the 24-hour recall. Since we need to estimate the between and within person variations, we need to use a linear mixed effects model in order to estimate all the parameters in the prediction equation. In the remainder of this talk, we're going to compare three possible study designs or diet assessment strategies for estimating true dietary intake. I call them study designs because the dietary assessment strategies must be decided at the design phase of a study. The first strategy is to use a single FFQ to assess diet. The second is to use one or more 24-hour recalls per subject. And the third is to combine the FFQ with one or more 24-hour recalls per subject. This comparison is based on a paper by Raymond Carroll and colleagues that will appear in the American Journal of Epidemiology. We're going to evaluate the study designs by their abilities to predict true intake. which is equivalent to their abilities to detect diet health associations when regression calibration is used to correct for measurement error. Ability to predict intake will be measured by a predictor's R-squared value. The R-squared value is defined as the squared correlation between true and predicted intake. Equivalently, it can be thought of as the proportion of variation in true intake that is explained by the predictor. So why is the R-squared value important? The R-squared value is a direct measure of the ability to predict true intake, and in particular determines the following properties: the variance of the estimated diet health association, the power to detect the association, and the sample size required to obtain the desired power for testing an association. We're going to base our comparisons on data from the Eating at America's Table study, or EATS. The study used representative sampling of the U.S. population and included 965 men and women between the ages of 20 and 70. 2 dietary instruments were administered in the EATS study: a 24-hour dietary recall and a food frequency questionnaire. 4 24-hour recalls were collected from each subject, and the recalls were administered 3 months apart by telephone using a multiple pass methodology developed at the USDA. The FFQ was the diet history questionnaire developed at NCI. We're going to look at the effect of study design on the prediction of 3 dietary variables: total fat intake, whole grain intake, and dark green vegetables. We're going to energy adjust these variables using the residual method to adjust for energy intake. I wanted to mention that Carroll and his colleagues performed a more complete analysis looking at a total of 10 dietary components, both unadjusted and energy adjusted. In our comparisons, we make the following assumptions. First, we assume that the 24-hour recall provides an unbiased estimate of true usual intake for each individual. As in previous webinars, we call this first assumption a working assumption, and we note that there's evidence that for at least some dietary components, the 24-hour recall is in fact biased. Nevertheless, we need to make such an assumption in order to make any progress towards solving our problems. I'll talk more about this assumption at the end of the lecture. The second assumption we make is that the 24-hour recalls and food frequency questionnaires have non-differential error with respect to health outcome. As I mentioned earlier, this is usually considered a reasonable assumption in cohort studies. That's because in cohort studies, diet is assessed at the beginning of the study before any health events have occurred. I want to mention that the comparison will not explicitly consider the cost of the study designs, but I will talk about costs later. Also, to simplify the comparisons, we're going to ignore the uncertainty due to estimating the parameters in the prediction equation. This is because 3 of the study designs require a calibration study in order to estimate the prediction equations, while the other designs don't require a calibration study. Because we didn't want to take this into account, we decided just to make this simplifying assumption. The study designs we're going to look at are a single FFQ from 1 to 12 24-hour recalls, and the combination of the single 24-hour recall a single FFQ plus 1 or more 24-hour recalls. Since the subjects in EATS only completed 4 24-hour recalls, we're going to have to simulate the case of 5 or more 24-hour recalls per subject. I also want to mention that the FFQ plus 12 24-hour recall design represents the best study design. And by this I mean two separate things. First, it's the best design among those we're considering, and this follows from the simple fact that adding information always improves prediction, or at least never makes prediction worse. And the second thing I meant was that we think that the FFQ plus 12 24-hour recall design is probably about the best one could hope for in practice without imposing an unreasonable burden on participants, although even this assumption may be overly optimistic. we're going to consider 4 research questions. First, does a single FFQ work better or worse than 1 or more 24-hour recalls? Second, how many 24-hour recalls per subject should one collect? Third, how much does adding the FFQ improve the performance of the 24-hour recall, and vice versa? Finally, if you already have a 24-hour recall, is it better to add another one or to add the FFQ? In our graphical comparisons, we're going to look at the data in 3 different ways. First, we'll compare the R-squared values for the different study designs. As I mentioned earlier, the R-squared value is inversely proportional to the variance of the estimated Diet Health Association. So if one has an R-squared value that's twice as large as another design, then the variance of the estimated association for the first design will be about half as large as for the other design. Second, we're going to compare the powers to detect diet health associations. Third, we'll compare the sample sizes needed in order to achieve a 90% power. As I said earlier, power and sample sizes are both functions of the R-squared value, so in some sense, the different representations are equivalent, but each provides a different way of interpreting the data. The comparisons are going to be relative to what I call the best predictor, the FFQ plus 12 24-hour recalls. So when we look at the R-squared values, we'll actually be looking at relative R-squared values. That is, the R-squared value of each predictor divided by the R-squared value for the best predictor. And I'm going to present results for women. The results for men were similar and are available in the paper by Carroll and his colleagues. Here's the first graph, which shows the relative R-squared values for total fat intake in women. The graph has a lot of information, so I'm going to go through it in some detail. The x-axis represents the number of 24-hour recalls in the study design, and the y-axis represents the relative R-squared value. Let's see. The green line in the middle represents the R-squared value for the FFQ, while the red curve on the bottom represents 24-hour recalls alone, and the blue curve on top represents the combination of the food frequency questionnaire and the FFQ. The food frequency questionnaire and 24-hour recall. So the R-squared value for a single 24-hour recall is equal to about 0.35 compared to about 0.5 for the FFQ alone and about 0.6 for the combined FFQ and single 24-hour recall. We asked earlier whether adding the FFQ would improve the performance of the 24-hour recall, and we see that it does in this example. The R-squared value almost doubles from 0.35 to a little over 0.6. This is equivalent to cutting the variance of the estimated Diet Health Association in half. Another question we asked was, how well does the 24-hour recall perform in comparison with the FFQ? So we can look where the red and green lines cross, and we'll see that the FFQ performs about as well as 2 24-hour recalls. When you have 3 or more 24-hour recalls, they perform better than the FFQ. A third question we asked was, how many 24-hour recalls per subject should one collect? Now, this is a somewhat subjective question because, as you can see, the R-squared values continue to improve whenever you add more 24-hour recalls. But we can also see that the slope of this curve becomes flatter as the number of 24-hour recalls increases, so that the improvement becomes smaller and smaller. In their paper, Carroll and colleagues concluded that 4 to 6 24-hour recalls seem to capture most of the information available in the 24-hour recall. And so here is the point where you have 6 24-hour recalls, and at that point you can see that the slope is starting to get flatter. In the second graph, we're looking at the power to detect association in a diet health study. Again, for total fat intake in women. The y-axis in this graph represents the power to detect an association, given that the power for the best predictor has 90% power. So again, our comparison is relative to what we call the best predictor. We can see that the power for a single 24-hour recall is about 45%. That's here. And we can compare that to about 60% for the food frequency questionnaire and about 70% for the FFQ and single 24-hour recall combined. Like before, we see that the food frequency questionnaire performs about as well as two 24-hour recalls. And one interesting thing to note is that the slopes of the curves are much flatter here than they were in the R-squared graph of the R-squared values. That's up here. This is especially true for the slope of the curve for the FFQ plus 24-hour recalls, the blue curve. This indicates that the increase in R-squared value isn't translating into a significant increase in power. And that's something to consider when you're thinking about how many 24-hour recalls to collect. So in this third graph, we're looking at the percentage increase in sample size needed to obtain 90% power to detect an association. Again, the dietary variable is total fat intake, and we're comparing each design to the combination of the FFQ plus 12 24-hour recalls. So in this graph, we can see that if you use the FFQ alone or two 24-hour recalls alone, you would need a 100% increase in sample size in order to get the same power as a study that used the combination of the FFQ and 12 24-hour recalls. I said earlier that we're not going to explicitly consider cost of each study design, but this is a plot that would be useful when you're actually considering the cost. In this case, a single FFQ would require about twice the sample size as the design that combines the FFQ and 12 24-hour recalls. Depending on the cost of administering the 12 24-hour recalls, the larger sample size may or may not be cost effective. And in between these two extremes of a single FFQ or FFQ plus 12 24-hour recalls, we can see that you would need about a 50% increase in sample size if you had an FFQ and two 24-hour recalls, while if you had an FFQ and 6 24-hour recalls, you'd need about only a 10% increase in sample size. So we've looked at three graphs for total fat intake. Now we're going to look at the same three graphs for whole grain intake. I wanted to mention that total fat is a nutrient that is consumed nearly every day by nearly everyone in the population, while whole grains is an episodically consumed food group. On any given day, about 70% of the population consumes whole grains. This graph shows the relative R-squared values for whole grain intake, and it's fairly similar to the graph we saw for total fat intake. The R-squared for a single 24-hour recall is about 0.3 compared to about 0.5 for the FFQ alone and about 0.6 for the FFQ plus a single 24-hour recall. So also we see that the FFQ is a little more powerful than two 24-hour recalls, but not as powerful as three 24-hour recalls. Something that I didn't mention before is that if you compare the red and blue curves, you can see that the lines become closer and closer together as more 24-hour recalls are added. This indicates that the more 24-hour recalls you have, the less the FFQ adds to the prediction equation. And this is the power to detect diet health associations for whole grains. A single 24-hour recall here has about 40% power compared to about 60% for the FFQ and about 70% for the combined FFQ and total and 24-hour recall. And here we see again that the slopes of the curves are very flat after about 4 or 6 24-hour recalls, indicating that additional recalls will not substantially increase the power. This is the percentage increase in sample size needed to obtain a 90% power for whole grain intake. We see again that the FFQ alone, or the 2 24-hour recalls, need about 100% increase in sample size to have the same power as our design having an FFQ and 12 24-hour recalls. Let's see, we can compare that to the design with an FFQ and 6 24-hour recalls, where you would need an increase of about 15% in the sample size. So finally, we're going to look at dark green vegetable intake. The graphs for dark green vegetable intake are quite a bit different from those we saw for whole grains and total fat. I wanted to note that dark green vegetables are very episodically consumed. On any given day, they're consumed by about 20% of the population. And in this graph, we can see that a single FFQ has a relative R-squared value of about 0.8, substantially higher than we saw for total fat or whole grains. I want to emphasize that this is a relative measure for comparing different study designs rather than different dietary components. So we're not saying that the FFQ estimates dark green vegetable intake more accurately than it estimates total fat or whole grains. What's actually happening is that the 24-hour recall does not estimate dark green vegetables as accurately as it estimates total fat or whole grains, so that by comparison, the FFQ seems to be performing much better. And this is a very reasonable assumption or a conclusion, since dark green vegetables are consumed by about 20% of the population on any given day. So as a result, 80% of the 24-hour recalls have zero intake of dark green vegetables. And that leads to relatively little information in each 24-hour recall. And as we can see here, it takes about 10 24-hour recalls to have the equivalent R-squared as a single food frequency questionnaire. I wanted to point out that we saw a similar pattern when we looked at fish intake and red meat intake. Fish intake is another food group that's very episodically consumed, but red meat is not that episodic. It's consumed by about 50% of the population on any given day. So this graph shows the power to detect associations for dark green vegetables. We see that a single FFQ gives you over 80% power to detect the association, compared to 90% power for the FFQ plus 12 24-hour recalls. So adding 12 24-hour recalls only increases the power by about 10%. The power for a single 24-hour recall, as we can see here, is quite low. And it takes about 10 24-hour recalls to have the same power as a single FFQ. So finally, this graph shows, excuse me, this graph shows the percentage increase in sample size needed to obtain 90% power for dark green vegetables. We see that you only need about a 30% increase in sample size to obtain the same power with a single FFQ as you have with the combination of an FFQ and 12 24-hour recalls. That's here. For the 24-hour recall alone curve, you have to have 4 24-hour recalls before you even make it onto the graph, as you see here. So for dark green vegetables, the FFQ is quite an important predictor of true intake. So we want to summarize our comparisons. First, we can say that in general, the FFQ performs about as well as 2 24-hour recalls. And as we saw for some dietary variables, like dark green vegetables, the FFQ performs better than 6 or more 24-hour recalls. We can also say that 4 to 6 24-hour recalls seems to capture most of the information that's available in the 24-hour recall. We also found that combining the FFQ and the 24-hour recall can lead to substantial gains over either instrument alone. And in most cases, adding 1 or more 24-hour recalls to an FFQ also provided significant precision. Finally, for dietary components that are very episodically consumed, like dark green vegetables, it's especially important to include an FFQ. Now we're going to talk about some limitations and other considerations. The first limitation of these comparisons, as I mentioned earlier, is that we had to simulate 5 or more 24-hour recalls. And we did this under the assumption that the quality of the recall would not drop off. That is, we assumed that the respondents would continue to respond and to continue to diligently complete their 24-hour recalls. A second limitation is that for the study designs that include just the FFQ or a single 24-hour recall, you need to have a calibration study of participants who completed at least 2 24-hour recalls in order to estimate the prediction equations. And for our comparisons to be valid, the calibration substudy must be large enough that the prediction equations can be accurately estimated. The most important limitation of our comparison is that we assume that the 24-hour recall provided an unbiased estimate of true intake for each individual. From studies with reference biomarkers such as doubly labeled water for energy intake and urinary nitrogen for protein intake, we know that 24-hour recalls are in fact biased for these nutrients. In general, if you incorrectly assume that the 24-hour recall is unbiased, 2 things happen. First, the diet health associations will be biased. Second, comparisons of different study designs will be invalid unless the bias of the bias is the same for all study designs. So we're going to look at the effect of assuming the 24-hour recall is unbiased when it's really biased by using data from the open biomarker study. The open study included 484 men and women between the ages of 40 and 69. Dietary assessment was done by a food frequency questionnaire, a 24-hour dietary recall, and reference biomarkers for energy, protein, and potassium. These biomarkers have been shown in feeding studies to provide approximately unbiased estimates of true intake. And here we see 2 graphs of estimated R-squared values for energy-adjusted protein in women. On the left-hand side are the R-squared values estimated using the biomarker as the reference instrument, while on the right-hand side are the R-squared values estimating using the 24-hour recall as the reference instrument. As we can see, the comparisons based on 24-hour recall are quite similar to those based on the reference biomarker. So this graph is for energy-adjusted protein in women. Now this is the same 2 graphs for energy-adjusted protein in men. In this case, we see that the 2 graphs are not at all similar. In particular, the graph on the left that uses biomarkers as reference instrument has a much higher R-squared value for the FFQ alone than the plot on the right that uses the 24-hour recall as the reference instrument. In this case, assuming that the 24-hour recall is unbiased leads to underestimation of the predictive ability of the FFQ. Here are graphs of the R-squared values for energy-adjusted potassium in women. In this case, we see that the 2 plots are quite similar, indicating that using the 24-hour recall as reference leads to quite reasonable estimates of R-squared values. And finally, these are the R-squared values for energy-adjusted potassium in men, and again, they are quite similar. So in summary, we found that in 3 out of 4 cases in the open study, using the 24-hour recall as a reference instrument led to very similar results as using the unbiased biomarker as a reference. In the 4th case, however, the results were quite different. Now, these results indicate that we need to be careful when using the 24-hour recall as a reference instrument. Conclusions about any particular dietary component may or may not be valid, but conclusions about general patterns that are consistent over many dietary components are likely to be valid. As I mentioned earlier, our comparisons didn't consider the cost of the different study designs. When you're actually designing a study, however, you will need to ask, is the gain in precision worth the cost of collecting more information? And by cost, we mean both the monetary cost of conducting the study and the burden imposed on the participants in the study. 24-hour recalls and food records impose substantial burdens on participants, while new automated versions of these instruments may reduce the costs, they won't reduce the burden on the participants. Here are a few other questions that we haven't addressed. First, how many 24-hour recalls can we reasonably expect the participant to complete before we start to get declining response rates or declining quality? Second, our study design comparisons were based on the EAT study, which used traditional interviewer-administered 24-hour recalls. Will the new automated 24-hour recalls perform as well as traditional 24-hour recalls? Finally, how will food records perform in combination with other instruments? We weren't able to assess this since the EAT study didn't have food records. In particular, will food records give us results similar to those for a 24-hour recall? Can we equate a four-day food record with 4 24-hour recalls? These are questions that we haven't addressed and can't really answer at this time. But there are biomarker studies currently underway that have been designed to answer these questions. These studies will have 6 automated self-administered 24-hour recalls, 2 4-day food records, and 2 food frequency questionnaires. They'll also have biomarkers of energy, protein, and potassium. And additionally, they will measure physical activity using an automated 24-hour recall 24-hour physical activity recall, and also accelerometers and fasting bloods and other information. Finally, I wanted to mention the possibility of using more than one food frequency questionnaire per subject. We've talked about having repeat 24-hour recalls, perhaps repeat food records, but what about repeating the FFQ? As I said earlier, one of the virtues of the FFQ is it has less within-person variation than the 24-hour recall or food record. As a consequence, there's less potential for gain and precision by adding the FFQ. This is because repeat application of an instrument is only useful for decreasing the within-person variance. Also, the use of repeat FFQs leads to some challenges in interpretation. First, if 2 FFQs are administered 1 year apart, does the difference between them reflect a random within-person error, or does it reflect a real change in diet? And second, if the true intake is not static but is always changing over time, how should we define true intake? What is the time period that is relevant to diet health associations? I'd like to summarize the main points of this talk. First, we saw that combining self-report dietary instruments can lead to significant improvement in estimating diet health associations. We also saw that regression calibration is an effective way to combine instruments. We saw that 4 to 6 24-hour recalls seem to capture most of the information that's available in 24-hour recalls. And we also saw that adding an FFQ to one or more 24-hour recalls generally improves prediction more than adding an additional 24-hour recall. Therefore, when designing a diet health study, one should consider using a food frequency questionnaire and 4 to 6 24-hour recalls to measure diet. Other factors such as cost and participant burden must also be considered and balanced with the need for precision and power. And finally, I wanted to emphasize that these conclusions apply to study designs for estimating diet-health relationships. They don't apply to studies designed to estimate population distributions of dietary intake. These are two very different tasks that need to be evaluated differently. In fact, in a 2006 article, Janet Tooze and her colleagues found that adding a food frequency questionnaire to 2 24-hour recalls did not substantially improve estimated population distributions. They didn't do a comprehensive analysis, and there may be situations where adding an FFQ could improve estimates of the population distributions. Nevertheless, their results indicate that a food frequency questionnaire will have at most a limited role in estimating population distributions. Thank you.
Thank you, Doug. We'll now move on to the question and answer period of the webinar. Thanks, Doug. We'll now move on to the question and answer period of the webinar, and I believe you just answered the first question, which was, will adding a food frequency questionnaire to 2 24-hour recalls improve the precision of estimated population distributions? Am I correct in saying you just answered that?
Yes. I would say that there's a possibility to getting a moderate gain, but it's not going to be as large as when you add 24-hour recalls, just because they don't have as much within-person variation.
Okay, thank you. So in the example you showed from the open study, did you also look at the R-squares, or were the R-squares for energy also assessed? Excuse me.
Oh, well, actually no, because we were concentrating on energy-adjusted nutrients, and of course you can't energy-adjust energy, so we didn't look at that. And well, that's all I can say now.
Okay, thank you. For cross-sectional data like NHANES, can it also be assumed that self-report instruments have non-differential error? And if not, what impact does this have for methods?
That's a difficult question. No, I can't. Typically, they say it's thought that for cohorts, the assumption of non-differential error is probably reasonable. For case controls, it's maybe unreasonable because of possibility of recall bias. That's when people who have gotten some health event, they remember their past diet differently than those who haven't had that same event. Cross-sectional studies fall probably somewhere in between the health event and the dietary assessment are taken contemporaneously. So there's definitely problems where someone might have developed some disease and subsequently changed their diet. So I would have to say it's a little more like a case control study in that you have to worry a lot about differential errors. So you have to be very careful when you examine a cross-sectional study.
Thank you. When you were dealing with the EAT study and you talked about truth, how did you actually estimate truth in that study?
Okay. In the EAT study, so in that study we had to assume that the 24-hour recall was unbiased because we didn't have any kind of biomarkers. And when we say it's unbiased, we don't mean that it's truth, but that it's truth plus some random error, within-person random error, that if you averaged over many 24-hour recalls for the same individual, you would get true intake. And so we used the measurement error model in which we assumed intake plus with in-person error, and we estimated all the parameters, and from that we were able to estimate not truth itself, but the relationship between true and reported intake.
Thank you. So far we have just one more question. Does adding a screener to a 24-hour recall or number of recalls have the same potential to improve precision and power as what you showed for adding an FFQ?
I'm sorry, can you repeat the question?
Does adding a screener as opposed to an FFQ have the potential to improve the precision and power when you're combining instruments?
Sound like Franz on the line. I would say definitely has potential to improve the 24-hour recall. We'd have to look at it. We'd have to actually look at it in a study to see if it performs well as a food frequency questionnaire, but certainly there's potential.
Thank you. We have no other questions, so thanks very much, Doug, and thanks to our audience for joining today's webinar. Please join us next week for webinar 11 when Dr. Lawrence Friedman will discuss combining self-report data with biomarker data to reduce the effects of measurement error. And thank you very much. And that concludes today's webinar.